is very much similar as alkane. So the minor modifications, it is the now no longer we pick the longest chain as parent. Instead, we pick the longest, but it must have the carbon-carbon double bond. And also with that carbon-carbon double bond with the lowest number, locant. Okay, so that's the way we name the alkene, the big difference. Give the double bond as the lowest number as possible. And the other part of the difference is the E and Z configuration, because the double bond cannot rotate. Then the substituent on the double bond can have the different, we call it stereoisomers. That's what is the EZ designation. And so pick the longest with the alkene as, so this is the example. This is the molecule. If the alkane, then we pick the those 8 carbons as the longest chain. That's named as alkane. But if there's as alkene, we need to pick the longest, but it must have the double bond as part of the parent chain. So that's a big difference. We no longer pick the longest, but pick it with double bond, because double bond is functional group. And the other part is the we give the double bond as a low number as possible. This rule is above everything. It is above any substituent. The rule is about substituent in the alkane. Okay, we give the double bond has the lowest locant number as possible. And so the parent chain, yeah, once you designate that, then the naming actually is relatively easy. This naming is a little easier than the alkane naming. If there's more than one double bond, we add the prefix right before the en. So for example, if the longest chain have 3 double bond, then the name is the heptatriene. So add the prefix tri right in front of the en. And then later shows what location have those double bond. And isomerism, we learned about cis and trans. Now we have more. Okay. Cis and trans is actually easy. And so these are cycloalkenes. The cycloalkenes for the smaller rings, it can only have the cis because the strain on the ring. For the larger rings, it can have a trans. So cyclooctene, it can have a trans configuration. The EZ designation it is based on the priorities of the group. If the high priorities, these are on the 2 carbon of the double bond, and each carbon have 2 substituent. And so between these 2 substituent, we pick the whichever group has higher priority, and the priority order, it is based on atomic number, exactly same way as in the RS, the chiral center designation for the priority of the groups. And so there's just two substituents on this carbon. This is the SU group. This is the fluorine atom. Fluorine atom has the atomic number that is 9. This carbon is only 6. So the fluorine have a higher priority than the carbon. And on the other carbon, you have a hydrogen, you have nitrogen. Nitrogen, of course, have a higher priority than the hydrogen. So after we decide the priority, now we see the F and N on the same side of double bond. On the same side of double bond, okay, if you apply to the hydrogen, and then that should give us cis. Okay. With the EZ system is more generalized. It can deal with when the carbon in the double bond does not attach to hydrogen. Okay, so if the two high priority on the same side of the double bond, such as this designated Z. Z is come from German zusammen, means together. If the high priority on the opposite side, not the same side of the double bond, then is the E. Antigen, so means opposite. So in a way, the E and Z designation is related to the cis and trans. Together, which means the hydrogen together on the same side of the double bond, that's cis. And the E means the hydrogen on the opposite side of the double bond, that's the same as trans. But EZ designation is much more all-encompassing. So basically cover more grounds, whereas the cis and trans, it covers only when the two carbon, each carbon has the one hydrogen. Has only one hydrogen, but only one hydrogen. Then you have a cis and trans. The EZ designation is much more covering more grounds. And so with EZ designation, then the naming compound is fairly easy. Okay, it would be very easy to. Later, we're going to see some examples, but you can see on the Zeppelin, there's some practice on the EZ naming, apply the E and Z in the naming. As we learned before, the cis and trans, the trans or the trans configuration have a lower energy than the cis because the absence of eclipse. Okay. The cis is where the big alkyl groups are in the exact eclipse position. So the energy is a little higher. And the trans, just on the opposite, have a lower energy. Naming alkenes, naming alkene, this is compound we can see there's we can name as this as substituent attached to the cycloalkane, or you treat this as the parent and cycloalkane as the substituent. So this would be cycloalkyl group. And so if this is a substituent, then this will be the parent. Longest chain that with double bond, that will be the parent. And so then the naming will be obvious. This, let me see. Actually, sorry, this would be this would be longest chain. Actually, the longest chain with carbon and give the double bond as a low number. So it could be either this is number 1 or this is number 1. But again, when you decide which one is preferred, remember we should give the alkene as a lowest locant as possible. So from here is better than here because from this as position 1, the alkene happens on the carbon 3. Okay, if this is the number 1, then the alkene happens on the number 2. So not this, but that. And then the naming will be easy. This is number 2, have a cyclohexyl, and 3 and 4. Number 4 have a 2-methyl group. So the naming will be 2-cyclohexyl, 4,4-dimethyl. And then there's 5 carbons, so pentene. The pentene happens on the carbon 2, so it's either 2-pentene or pent-2-ene. Let me see. Oh, okay. This is a. I think this naming has some problems. Just kind of debatable. Forgot where to get this naming. It's a long time. The should have the parentheses, have the E. Anyway, we decide this is going to be number 1, 2. This is one way to name that. I think the better way, different way is on the, we pick the, like a circle, those as the longest chain. So that'll be pentene. Parent should be pent-2-ene. And that way the it'll be 2-cyclohexyl, and then the 4,4-dimethyl. And then for the EZ designation, that you put in the front, in parentheses, with a hyphen, separate. So as for the E and Z, we decide between these two groups. This obviously cyclohexene have a high priority, so there it is, high priority. Labeled high priority between these two. And then between this and here's hydrogen, apparently this is tert-butyl. It's a big high priority group. High priority than the hydrogen. So now we can see the high priorities is on the opposite side of that double bond, and then that should give us E, capital E, for naming this compound. So this is the one way to name that. And the other way, according to this slide, I need to check the book. This is the this is different way from what we named the first example. It looks basically the same point to the same structure, but this one gives the longest chain, only butene. It's either 1-butene or but-1-ene. Okay, so that's the difference from what I did here. We pick the longest chain with the carbonyl and count the 5 carbons as the longest.
So is the answer on the PowerPoint, is that, would that be acceptable, or is the pentene like more correct?
I like the pentene 2 better, but let me check the. So my conclusion is I will go with whatever on the red. This is the kind of alternative and make the longest parent shorter. I don't like this as much.
Thank you.
Yeah, it's come from the old PowerPoint. Not sure when this been made. Okay, so these are. This exercise is about the allyl. This is the allyl group, and this is vinyl group. I don't see this kind of questions in the new edition anymore. These are completely old PowerPoint. So basically, it's about some of the naming for the double bond group. It's basically alkene as a substituent. Okay, we have a special system named as this is allyl, I think. Oh, allyl group. This is vinyl group, and this is a phenyl group. Next semester, you'll see more about a phenyl group. It's more reactions about aromatic compound. And this is a benzyl group, okay. Benzyl group, related to benzene. Anyway, this will be not in our Zeppelin homework. I don't see this kind of question in our Zeppelin homework, so I will not cover this, the allyl whatever group. You might be able to see that from the, let me see that new 3rd edition. I don't see those kind of group anymore in the naming. The book mentioned about those groups, but I don't see the in the actual naming exercise. Also, it's not in our Zeppelin homework, so don't worry about it. That'll be, oops. Okay, so for the nomenclature, that's how much we'll go. We're gonna not get into much nomenclature. I don't like nomenclature in general anyway. The nomenclature is almost a system. I try to differentiate, and categorize, and that's kind of a politically not quite correct. We try to categorize people, just like how we categorize compound, or vice versa. Okay, so the chapter 8, this is the main focus. All the reactions. And all those reactions, reason why we deal with them, to learn them, it is because this is how the alkene becomes so useful for organic chemistry and for human civilization as well, because nowadays we use plastics in all different kind of places. And almost all the plastics start from alkene. And there are many reactions, not just start from alkene, 1 or 2 steps to get to product. Sometimes require a lot of steps. And each step, how this reaction takes place, we need to understand. The alkene reactions, it introduce another load of new reactions. And to me, those are fascinating. And this, by the way, is the reason why the organic chemistry is just more interesting to me, because you can just change some of the reaction conditions, some reagents, and you can get a completely different product. So when you learn this chapter and try to do homework, keep this in mind. The organic chemistry is very important, very useful, and the reason because it can go through some very fascinating, but can be bewildering, the mind-blowing changes. So take some time to get used to. And so in this chapter, the alkene reactions. Now the alkene start from the double bond. By adding a group, it can become all saturated, all single bond. And so essentially it is from a 2-dimensional molecule becomes 3-dimensional. And the 2 carbon might have both be able to add to the same group. You end up have 2 different products. So we need to know what is the reaction pattern, which one is the major product under what reagents and the reaction conditions. And so the residual selectivity, which means 2 different locations, and they go through similar reaction, give you 2 different products. That's a residual selectivity. The stereochemistry, it is since alkene is a 2-dimensional molecule. When we add the new electrophile, when we add the electrophile to the double bond, the electrophile can attack from both sides. And attacking these 2 sides might give you 2 different products. And of course, we'll give you the RS, different enantiomers, the pair of enantiomers, RS, depends on which side is being attacked. And there's something more. And so the reaction mechanism that you are supposed to know very well and predict the product. By the way, the residual selectivity stereochemistry, it shows what kind of preference the product will be. And just memorizing the preference, it's kind of hard. But to understand the reaction mechanism, how does the carbocations and maybe some other reaction intermediates is favored for certain reaction pathway is very important. Understand the steps, the key steps in those reactions. And these 3 reactions are we need to know very well. First one is the halohydrogenation. The second, hydration, is that adding water. Hydration is just adding water. It sounds very simple, but it's actually not just simply add water to the double bond. It goes through a process. And then the halogenation, adding the halogen elements to the double bond. So these 3 reactions are the main focus. And so these are the reactions might take place. We have all different names. The first one, double bond, add the HX. the hydrogen halide, and you have these two pieces add on two separate carbons. And so this is the very important, we call hydrohalogenation. And then can be adding water, adding water H and OH. It's just simply hydration. And then the adding hydrogens, adding hydrogen element, it is a hydrogenation process. This process has been used in the industry, in the food industry for a long time, because chemists develop a way to add hydrogen to the vegetable oil, turn into the artificial butter, the margarine. Even though later we'll find out some of the trans fat come from this process, can be very dangerous for health. But that's actually we're making use of the vegetable oil, turning to more buttery, more solid, higher melting point. It is through the adding the hydrogens. Adding the halides, adding halides is very useful reaction, and the two hydrogen on each. And then we can add in the HOX. The name of this X is a halogen, so this is basically hypohalous acid. The general name will be hypohalous acid. The low amount of oxygen in the formula. But anyway, this region add to double bond, it is a halogen and OH add separately in the reaction. And finally adding the OH and OH. This reaction, these two are the less important reactions among all these addition reactions. The first four are the most important reactions we need to understand. The last two, we just need to know what will happen in the product. And these last two will be easier to understand if you understand the first four reactions. Okay, so that's the four reactions. The first one. The addition reaction is a Lewis acid base reaction. The Lewis acid base is based on the lone pairs. The lone pair donor is a Lewis base. Lone pair acceptor is Lewis acid. So the reactions, the alkene as a Lewis base, okay, alkene as a Lewis base, give electron to the proton and to form the carbocation. So that's the this is the adding proton reactions. And also the double bond, since I have a high energy pi electrons, again, it acts like a Lewis base, can give the pair of electron to a electrophile, okay, electron that is attracting electrons and to form bond. So we'll see both. We'll see both in our reaction, addition reactions. And so the addition and elimination is reversible, is reverse the reaction. Under certain conditions, it can coexist, reach equilibrium. The addition reactions entropy decrease, okay, the entropy decrease. So therefore, the addition reaction is favored at low temperature, okay, at low temperature. And so the addition reaction entropy decrease, and the exothermic reaction, therefore the low temperature is ideal for the addition reactions. Okay, so energy analysis. It's not that important in this chapter, so we can fast forward. The first reaction is hydrohalogenation. This is the reaction the alkene becomes the halides, alkyl halides. And so when we have a symmetrical alkene, adding the hydrogen bromide at low temperature, again, you can see addition reaction really like low temperature. And also low temperature is slow down the reaction, make the reaction more concentrated on the major product. when you have a high temperature, all reaction go fast. You might end up a bunch of all different reaction product, including rearrangement. So it's very complicated. Low temperature, even though slower, but you can get only very limited amount of number of byproduct in the reaction. And so this is the symmetrical alkene. Give a single addition product. Unless rearrangement comes from the carbocation. Okay, symmetrical, when we add hydrogen here or here, and later followed by adding the bromide, you get the same only one product. Okay. If you have an alkene that's asymmetrical, which means you draw a line across the double bond between the left and right, the substituents are different. We should get two different products. Okay, we will get two different products, and there's a rule to predict. We do have one as a major product. Okay, the major product. So, for example, these two carbon between left and right are different. So when we add a hydrogen and then add the halides, we might the halide can be here, or halide can be here. Which one's the major product? The Russian chemist Markovnikov, he found out there's a general pattern. Which one's the major product? In general, the hydrogens tend to add to the carbon that already have more carbon. The hydrogen attached to the carbon that has already had more hydrogen. So that means you can see this is the asymmetrical alkene. On the right hand, there's more carbon. On the left hand, there's less carbon, more hydrogen. By adding the hydrogen halide bromide, the hydrogen tend to add to the carbon that already has more hydrogen. And the bromide add to the other one. So this we call a Markovnikov rule. In the last chapter, in the chapter 7, we learned about a Zaitsev rule versus Hoffman. And here we have a Markovnikov. Actually, Zaitsev is also a Russian. And the Markovnikov is also Russian. And so the, or in other words, is the halogens add to the carbon that has more carbon attached. So that's the, this will be the major product. This. The minor product will be just opposite. Minor product, it is bromine add to the other one. Bromine add to the carbon that is with more hydrogen. This is minor product. So now we have these two reaction competition, and we need to understand why. The reaction mechanism through the kinetics study shows us this reaction is a second order reaction. It's first order for alkene and also first order for the halides, hydrohalides. And the slow step, okay, if this is slow, is a two-step mechanism, the slow step must have these two together. So that's, okay. I'm here to write down the reaction mechanism. How does this reaction takes place? Use arrow pushing. Okay, so the reaction, you can see this is reaction rate law. It shows us the second order. So the slow step must have these two together. And slow step, it is these two, the pi electrons together form bond. So this is basically a nucleophile. alkenes nucleophile because they are rich in electrons. They attract the positive part of the molecule. So our first step, it should give us a carbocation. Okay, the carbocation. When this double bond attack the hydrogen form carbocation, the hydrogen can either attach to here. If hydrogen attaches here, positive charge over here. If hydrogen attack here, this is hydrogen, then positive charge will be here. Between these two, this carbocation is secondary carbocation. This carbocation, if this one has a positive charge, is more stable, it's tertiary. So, because tertiary carbocation are more stable, it should have a lower activation energy. It should be easier to take place. So that's the first step product. The other product is the chloride ion. So that's our first step. And then the second step, look at our final product. Chlorine is attached to the tertiary carbon. So it should be one step. And that will give us the final product. Very nice. It is two-step reaction mechanism. Very simple. And it's two steps. So the energy diagram shows you that first step is more difficult because the intermediate, the reaction intermediate is high energy state. Since this one high energy based on the Hammond postulate, the transition state for the first step should be also in a higher position. Okay. Because reaction intermediate is high energy. And so that's the proton transfer first step. The next step, positive negative charge, they attract. So relatively less resistance to form the final product. And so basically the main product can be explained by the stability of the carbocation. That shows you why. Basically these are two scenarios with the same asymmetrical alkene react with hydrohalides. First scenario is when the hydrogen attached to here to form bond. This attached to hydrogen. You get this as a carbocation. And the other product is halides. And the other way it is hydrogen attached here. This will have hydrogen. So you get a different reaction intermediate. As we learned before, the tertiary carbocation, which is here, is more stable because of more hyperconjugation with the methyl groups. Hyperconjugation. Whereas the secondary carbocation, you have only two alkyl groups, and only this methyl give a hyperconjugation to stabilize. So therefore, it's not preferred. This is high energy. This is low energy. So that's why the lower energy intermediate give you more product. So that's and the reaction energy difference because the stability causes high energy of the secondary carbocation. It causes high activation energy. That makes it slow down. This reaction will be slow, slower than this reaction. So that's why you got two different products. And so the transition state, this diagram is very interesting, shows the transition state. The transition state is basically you have either hydrogen attached to this carbon, transition state, or hydrogen attached to the other carbon. So anyway, these explain very well because the tertiary carbocation is more stable. And also the alkene attached to the HCl from the two-dimensional alkene becomes three-dimensional structure among these two carbons. So it might give us a stereo chemistry. So basically, we might have the RS product between these two. But again, this reaction, because the carbocation is a trigonoplanar structure, the last step of reaction, halide react with the carbocation, cannot happen on both ends. So that's why, in the end, the reaction product is a racemic. The halide with this carbocation, the halide in the last step can either come from the top or from the bottom. You end up has a pair of enantiomers. So the reaction no stereochemistry specific. Rearrangements. Okay, the rearrangements in the substitution and elimination, we see them many times, and actually is the same pattern shows up here. Depends on the carbocation is next to a quaternary or a tertiary. It can be either a methyl group shift or a hydride shift. It's just like we did before. And so here we have this reaction. We add this alkene, by the way, is terminal. Okay, terminal alkene, you have two hydrogen here, and here's one hydrogen. And so the first step is always to form a much more stable secondary carbocation. So the reaction mechanism is the first step. This attack the hydrogen, the chloride, hydrogen chloride in this case. All right, so we have that. And because the hydrogen can either add to here or add to here. If hydrogen added, then the positive charge should be on the other carbon. Okay, so if hydrogen add to here, cations here, positive charge here. If the hydrogen add to here, the positive charge here. This is not good carbocation. So that's why the hydrogen must be attached to this carbon to give you a secondary, more stable carbocation. Hydrogen add to here. Okay, let's show this hydrogen. And the carbocation is here. So that's our first step. And if you look at the reaction, that'd be a problem. You can see the double bond here, and after the reaction, there's no more double bond. So that must be the addition reaction. And the addition reaction, if you look at the final product, the chlorine is on the tertiary carbon. But in our reactant, the double bond is not on this tertiary. It's not coming. Double bond is not here. So the reaction must have a carbocation shift location. And shift location happens, it's just like what we did in the last, the chapter 7. Carbocations here. Secondary, not very stable, but it's better, much better than primary. And the carbocation next to a tertiary carbon. This is tertiary carbon, which means this carbon linked with 3 carbons, and you have 1 hydrogen available. So same thing happened, the hydride shift. I have a hydride shift. Okay, I have a hydride shift. Okay, we don't need to show the hydrogen anymore, just kind of incorporate into the line structure. Hydrogen now is here. And the carbocation, because the hydride left, take away the pair of electrons. This is positive charge. Hydride shift becomes a new carbocation. It's more stable, tertiary. And from here to here, just in one more step. The halide that is in this, that's formed in this reaction, it'll nucleophilic attack. on the carbocation. Gives the high final the halides. And this reaction is a major product because the tertiary carbocation is much more stable. Secondary carbocations is not as stable as tertiary. And rearrangement. Okay, this is the same reaction. What do we find out from the research? This product, by the way, this product is formed without rearrangement, no rearrangement. No rearrangement. You got a 40% product, no rearrangement. The rearrangement product, even though I have one more step, it is more than the no rearranged. So this kind of reactions, we need to know and be able to write down the reaction mechanism. But in reality, it's not useful because this reaction gives you two products and almost 50-50. Then you have to show all the hard work to separate these two. It's not useful. The synthetic utilities.
Professor, would that one with the 40% be considered the minor product then?
It is minor, but still a little too much. The typical minor, I would say less than 30% is the, you have a real major product. But in this situation, you have these two very close. That's why it's not very useful. Yes, it's still minor product. But the I would not ask you to predict which one's a major product because the reaction without a rearrangement, you have less steps. It should be faster. But the rearrangement, even though it's one more step, the carbocation is much more stable. So it's very competitive, even though the some more steps. In real life, we do not ask you to predict which one. So you have a rearranged and unrearranged. You don't need to worry about which one's major and minor. But we might show you this is the product and ask you what is the reaction mechanism. Write down the steps. That's typical as in our Zeppelin homework. And yeah, know the reaction mechanism, how this is formed. The selectivity also depends on catalyst. This reaction, by the way, this reaction is when we add the peroxide. This peroxide is organic peroxide. You have the so basically it's almost like an ether. It's almost like ether. You get an alkyl group, and there's peroxide bond. This is peroxide bond, very unstable. And when you have this present in the reaction, it will give you the Anti-Markovnikov product. Even the hydrogen peroxide can also be as effective, give you Anti-Markovnikov reaction. And so the this reaction after the second midterm, we'll get into we explain the reaction mechanism is because the free radicals, this is actually a free radical reaction. And anyway, this is a reaction in this chapter. As I check our Zeppelin homework, we did not involve this kind of reaction pathway, so not to worry about it. But just keep in mind, this reaction with peroxide will give you the anti-Markovnikov. So whatever Markovnikov hydrogen add to the carbon with more hydrogen, and the anti-Markovnikov gives you just opposite. So with HBr, and you can see this, you have these two carbons. One has one hydrogen, the other carbon no hydrogen. So the addition should be hydrogen attached to the one with more hydrogen. The hydrogen will be attached to here, and the bromide attached to here. This is the only product. Anti-Markovnikov give you complete different reaction. Even though we will not cover in our assignment or quiz, just kind of know. The after second midterm, you'll see this kind of. We'll spend more time on the reaction mechanism about how this happens. All right. The second one is the hydration reaction. Okay, the hydration reaction. The good thing is, it's pretty much follow the same, very similar reaction mechanism. Goes through carbocation and then Markovnikov. So this whole morning we're going to go through the Markovnikov. The hydration reaction is not easy because the water has a very strong bond between the hydrogen and oxygen, very strong bond. So we cannot really expect the pi electron just attack the water and directly add the proton to it. The reaction acid is required. Okay, the acid catalyst is required. That makes the protonation process, adding proton process, much easier. And the acid to be used is very important. We cannot use the other hydrohalide acid, even though the acids are also very strong because they have halides. The halide might give you a different product, will not give you the alcohol as a product. So the acid in this reaction typically uses sulfuric acid. Sulfuric acid gives you the protons, and the bisulfate ion won't be involved in the reaction. And this reaction is Markovnikov. Okay, the hydrogen attached to the one that already have more hydrogen. And this add the OH. Okay, it's just like Markovnikov. And so the kinetics, the structure of the alkenes, and this is kind of shows you which kind of alkenes are easier or faster to react. This is both carbon have no alkyl group. And the reaction, if this one set as rate as 1, then the alkene with 1 methyl substituent, this reaction is 1 million times faster, much faster. And the product is a Markovnikov product. And if this carbon linked with 2 methyl group, the reaction is another 100,000 times faster than the single alkyl substituted alkene. And so this can be easily understood because the stability of the carbocation. We have a tertiary carbocation is much more stable, and therefore the reaction much faster. And so anyway, the reaction mechanism is very similar. Since we add the acid as catalyst, and there are protons in the solution. So first step, the alkene attack hydronium. Very important. Where does the hydrogen go? Okay, the hydrogen should attach to the carbon with more hydrogen. That way, you form a much more stable tertiary carbocation. Hydrogen must be on the other carbon. And then the next step, in the solution, there's a water as a solvent, and water as a nucleophile is a fairly weak nucleophile. It reacts with the carbocation, and the product give you the protonated. It'll be a protonated alcohol. They call it oxonium ions, or it's very similar to a hydronium ions. Very similar. It's protonated. Probably alcohol. And since it's protonated, to finally become the alcohol, the free alcohol, you need to lose the protons. And again, in this reaction, water is a weak base. You can take away the protons from the alcohol, give you the final free alcohol. This reaction, we need to know how to write. And so this, for the reaction between alkene and hydrohalides, It has only about 3 steps, 4 steps if there's a rearrangement. With hydration, there's more steps. There's 1, 2, 3 steps. It has the 3 steps. Oh, the hydrohalogenation have only 2 steps, 3 with rearrangement. Here it has 1 more step because it has the last step, deprotonation. Okay, this step is not existing for the hydrohalogenation reaction. Okay, so that's the reaction mechanism. It's very similar. This last step, deprotonation, is the only difference between this and the reaction mechanism we just went through. Thermodynamics. Because these 2 reactions, it can be addition taking place, give you the alcohol, and the alcohol can go through elimination, give you the alkene and the water. The entropy factor is the main factor. The forward reaction is exothermic. Okay, forward reaction exothermic, and entropy decrease. So to favor the addition reaction, low temperature. Okay, low temperature, it favors this kind of reaction. And also, since the reaction exothermic, it's always easier takes place. Low temperature just to make it less likely to reverse. High temperature, it favors elimination. If you remember in chapter 7, alcohol will go through the concentrated sulfuric acid at high temperature. It can reverse back to alkene. That's high temperature and concentrated acid. For the addition, we need a diluted acid and low temperature to make it a reaction favor the hydration. And so that's the difference between these 2, the temperature effect. The stereochemistry is when you have a asymmetrical alkene. 2 and the alkene are different. And again, the Markovnikov is OH add to the carbon with more carbon. This is where the OH add to. These 2 products, 50-50. Pair enantiomers give you exactly 50-50 because carbocation is a trigonoplanar. No difference when the water attack to the carbocation from one side versus the other side. No difference. The hydration reaction is very useful because the crude oil, it has a numerous amount of hydrocarbons. And there's most hydrocarbons are saturated. There's some benzenes going on, but the refinery, the oil refinery will go through the high temperature decomposition reaction, eventually give us ethylene, which is another name is ethene, a 2-carbon alkene, and it can becomes to produce ethanol. It can also make many other plastics, polymers. The polyethylene is basically the polymer made of ethylene. So that's the hydration reaction. We have a hydrohalogenation and hydration reaction. Next reaction, this reaction is getting complicated. Today we just started, but we'll not complete this session. Next time we'll continue on this. This is the other way to make an alcohol. In addition to the acidic catalyzed hydration reaction, this reaction is more useful in the high value synthesis because the reaction involves mercury as a catalyst. It's toxic and more expensive to deal with, but the stereochemistry is more specific, more useful. Okay, so the reaction condition is we add the mercury 2 acetate and with water. And the next step, we use a sodium hydroboride, as a reducing agent to remove the mercury in this reaction. And this reaction is also the Markovnikov, but this reaction will not go through carbocation. Therefore, no rearrangement. You get only one product, very nicely and clean. And so the reaction still, you can see, is a Markovnikov product, but the mechanism is completely different. So this reaction, the slide shows you many steps in the mechanism, but for our class, we need to be aware of this reaction condition. Remember this reaction condition. It has two steps. First step is the mercury acetate react. It forms a complex, a reaction intermediate. And next step, the hydride from the boron, remove the mercury in the reaction. So this reaction, the steps. The first, this is mercury 2 acetate. Mercury 2 or Mercuric, if you remember in the intro chem, it means a high charge state. Mercury have a mercury 1 and 2. These two are the most common. Mercury 2 is a high charge state, so we call them Mercuric. The mercury 1 is Mercurous. Mercurous is mercury 1. Anyway, mercury is acetate. This bonding is supposed to be ionic bonding, but it's because acetate and mercury is kind of weak base, so the bonding between these two is sort of covalent, half covalent. Mercury, the mercuric, it can form a bonding with acetate, and it is basically partial dissociated mercury 2 ion. Okay, it's partial dissociated. Together still have one positive charge, but mercury is still bound with one acetate. The acetate is dissociated. So it actually gives us a mercury cation. The mercury cation has positive charge, so it is an electrophile. It's attracted to the electrons. And it attracts the lone pair of the electrons, so it's a Lewis acid. And so the reactions happens. The mercuric cation, it attacks actually the alkene electrons, form bond with the mercuric, form a reaction intermediate. And so the between these two, the mercury lone pair can either bond with this carbon or the other carbon, and they both can exist. And so they form kind of a three-member ring. We call it three-member ring reaction intermediate. Reaction intermediate. And the nucleophile in this reaction is water. The water will attack, because we have this as a reaction intermediate. Water can attack either here or here. To explain final Markovnikov product, the nucleophile must attack the carbon with more carbons, because the positive charge is slightly better stabilized here on this carbon. This one is slightly better stabilizing the positive charge. That is why the nucleophile attack on this carbon. So once attack, which is a water attack, give you another reaction intermediate. This is also reaction intermediate, and nucleophile is attacked on this. This is a key step to explain why you have Markovnikov. Reaction intermediate is the triangular shape. We call it three-member ring, 3-member ring reaction intermediate. And finally, the last step reaction is the sodium borohydrate. Sodium borohydrate react to remove the mercury from the system. So basically, find a hydrogen replaces mercury with hydride. It's a free radical reaction, so we don't need to worry about it. So anyway, the reaction, if we go to the oxymercuration and demercuration, this is what we call this reaction, demercuration, to remove mercuries in the system. Demercuration reaction gives us the Markovnikov product. By the way, this reaction, if you remember from the acid catalyzed reaction, it will easily rearrange, give you completely different alcohol. But because we're using mercuric acetate and the boron to remove the mercury, we got only this is a major product. This is the amazing difference between the mercury catalyzed reaction versus the acid catalyzed reaction. Acid catalyzed reaction is very prone to rearrangement, whereas mercury catalyzed, you got only this product, very nice, no rearrangement. And you can see this is basically acid catalyzed reaction. It gives you completely different alcohol. It's just because after rearrange, carbocation is much more stable. So this is the 2 steps, oxymercuration and demercuration reaction.